Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my image to text AI. So the idea is we want to take some form of input and turn it into like a picture of some sort and turn it into ASCII. So let's say, hold on. I just need to show an example, but my environment isn't set up, so let me just pull that up real quick. The idea is that we might have like a picture that looks like something like this, and we might want to basically turn it into a sequence of like ASCII characters that looks like this. Hopefully this runs. Yeah. So here we have like, sorry, this is the wrong input. Something that looks like this. Much better. So this guy, you can kind of see that like he's got like the same kind of shapes in here. You can kind of see like brighter sections have like more filled in characters, darker sections are darker. And what we want to do is we want to try to get like the best version of this we can get. So what we're doing right now is we're just kind of like no AI involved, just taking the brightness of any given like area of the image and saying, well, how bright is it? And if it's brighter, we'll pick a character with more pixels filled in. Great. But you would kind of think that you could do better, right? Like characters have shapes, and you would think that if you could fit the shapes of those characters to the like contours in the original, you could get like a better accuracy for the same amount of samples. And so, you know, you think about that, you go like, well, what's like the like naive approach here? Say we have like a grid of pixels, right? So we have like, you know, 5 by 5. Oh my god, it's so bad, but whatever. And say we like fill in, you know, some of these guys so that it like looks kind of like a 1. Like you would think that picking the number 1 here, if the font matches this sequence, would be like a better fit than picking another character that has like the same amount of pixels filled in. And then you look at this and you say like, well, if we were going to try to map all input sequences, you'd have like the like bit depth of each pixel times 5 to the power of 5 times 5. That's how many options you have. So you can't like just pre-compute every single like input that you'll have and try to pick a character from that. Okay, so you could like every time you see a sample, try every single character and see which one's best. And that's like maybe not too bad, but if we start trying to like expand into like a ton of Unicode characters, then all of a sudden that might start looking a little lame. And then you start to think about like dithering. So if we have like a gray area and we have like only black and white pixels, like if you filled in every other pixel, just say that there was a character that like looks kind of like this, you might want to like how do we determine that's better? Well, you might want to do like some like blurring of the glyph and see like, oh, does the blurred vision match, and how much does a blurred version match versus something else? So there's all like these sorts of like complex rules that you might make up. And the thought is we make all these rules, right? Maybe they're expensive, and we train a neural network to kind of compute those rules efficiently. And so the idea is that maybe we could get a answer that gets something more complex than what we are currently doing, faster, and works okay. So that's what we're working on. And right now, kind of like the state we're in, is we have like the world's shittiest neural network. So what we have right now is we just hook up each of these pixels into the input of our neural network. So we have like, you know, pixel 1, pixel 2, pixel 3, all the way down. So this is like in our samples, in this example, we'd have like 25. And we just have an output of our neural network that's like character space, like character period, character colon, character at sign, essentially. And we just like connect every single pixel to every single one of these outputs. And it's making rules that's saying like, hey, I'm going to multiply, you know, if for this one, he's going to say like, I want all of these guys to be big. And for this guy, he's going to be like, I want all of them to be small. And these guys in the middle, he might say like, oh, I want, you know, something in the middle. And we were thinking like that should work. And we were kind of struggling with that last stream. And I couldn't help myself. I try to avoid working on these things like off stream because I think it's important to like, or it's like more interesting, I should say, to show discoveries and real discoveries online. But I couldn't help myself. I was a little curious last night, and I tried just taking my images and say we parse these images and they're like they're stored as brightness values between 0 and 255, right? Like what with a thing that fits in 8 bits. And so if we fed those directly in as 0 to 255 into the network, we got something that looked kind of like, this. So that's not really close to our like expected thing, right? How do I go back? Right, like we've got like a lot of like characters that we don't want to see in there. It's not like matching cleanly. Like it's not trying to do @ signs, not trying to do A's. And if I put my images into like 0 to 1 instead of 0 to 255, it starts to look like a lot better. I can like stop this training one sec. Let's just right, like for the same amount of training time, that looks like a lot better. It's getting a lot closer. It's got like the colons where we expect them to. Where'd my correct? This is what it's trying to get to, and this is where it got. And it's like you can see like a lot closer. And so my question for today is, why the fuck is that happening? And so I think that what I want to do is I want to like inspect the training in some way and try to just build an intuition on why that would work. Because in my current mental model, if every single one of these lines is just a multiplication, I would think that if the input is like 255 versus like 1, all that should happen is this weight should get like divided by 255. So why is that not happening, essentially, is my question. Yeah. And so let's just start taking a little peeky. So I guess we're at 6 minutes and 50 seconds into stream, and we should figure out what do we want to do first. What do we want to do first? How can we debug this? And so I think probably like the place to start is like just look at the weights in success case, and maybe try to, let's just do the stupid thing of dividing them by 255 and then passing in the original input and seeing if that works, right? Because then we can say, well, if we just take our weights divided by 255 and it works correctly, then we know that there's something like more interesting going on about like the training in the case where we have inputs in the range 0 to 255. So I actually shouldn't have canceled that training because we need to extract those weights. And I guess the first thing to do here is actually to like save weights after training, because right now we just kind of like we train and then we hit like Control C to stop the training, and all of our weights go away. So we need to find a way to like write them down, which I think there's a way to do in PyTorch pretty easily. There's like some sort of like PyTorch save weights. There's got to be a way to do that. Otherwise, people wouldn't train neural networks. Saving and loading models. So you have a thing, and they have a state dictionary. Is there no like? Oh, here we go. Torch save state dict, torch load state dict. Okay, so that should be pretty straightforward. Pretty straightforward. So I guess what we should do is just every time we write it down a sample image, every 1,000 iterations where like network's getting closer and closer to figuring out the right answer, theoretically. And on each of those, we like just dump the output just so that we can like look at it later. And so while we're here, we might as well just say, well, we'll save what we had. And so we can here say, what did they do? Model state dict this. And we need to save it to somewhere. So we will save it to like the iteration number dot, what do they like? Is there like a file extension for this thing people use? State dict, state, that seems reasonable. I don't know. Yeah, we'll save it as like state dict. And we have to format this with the iteration number. And then when we start training, we should be able to like load our initial weights. And we should be able to just say net load state dict. What did they do? Did they have to like, they just put torch load path. Okay, cool. Cool. Which means that in our argument parser, we need to be able to specify initial weights. And the default is going to be nothing. And it is not required, which means that this guy, he might be none. And so we should only load him if initial weights is not none. Okay. Boom. Easy. And so now I guess we just have to test this by quickly training something and then loading it and seeing if like the training continues in the same spot. Okay. So we will train. We will give it a little bit of time to write down at least a couple iterations. So we see he did write something down. And let's just give him a few seconds. Let's see, last time we got to like iteration 1000, it was already looking like pretty decent. So we can probably just get away with trying to shortcut, because a lot of neural network training seems to be waiting, and which isn't very good for a stream. So hopefully we can like maybe decide what we want to do, start implementing that in the background, and from there keep moving. Okay, so here we had a 1.0925 loss after our first 1,000 iterations. That looks pretty good. And if we then cancel the training and run it again, oopsies, where was I? Train, but what is my command line for loading those weights? Initial weights is going to be 1001.stateDict. Okay, so we gotta be careful here, because as soon as I start training, it's gonna start overwriting stuff. So maybe we should actually also in our training thing add, like, force ourselves to specify an output directory, so that I don't accidentally like overwrite stuff. Which means that here in our main we'll take an output directory. Did I call it output dir? Yeah, output dir. And I guess we'll just say, we'll turn this guy into a path. So output dir is a path of output dir, because his initial thing will be a string, and paths are a little nicer because you can use these like just kind of like quality of life things on them. Pathlib import path. And now just everywhere where we write stuff, I guess first we need to make the directory. And exist okay is false by default, parents is false by default. I think that's fine. So we'll just make the directory, and if the directory already exists, it'll be like, fuck you, already exists. Which means I guess maybe we should put like a little nice error in that case. So he raises. Does he raise something? File not found error. I guess we'll just find out. We'll find out pretty quick, and we'll adjust the error message later. And okay, so now anywhere where we would use this, we would just say output dir / this, and here we take in the iter, and here we should also take in the output dir, I guess. And when we save it, we save to output dir / this. Easy. Easy, easy, easy. Good enough for now. So let's just try running that really quick. And he's going to say immediately, hey, you didn't specify an output dir. So I can say output dir test loading, and our initial weights will be 1001 state dict. Okay. So nice. Okay, nice. Things are being saved into that directory, and we can actually check now that the first iteration before we have done any training looks pretty reasonable. So saving and loading our weights seems to be working correctly, and from there that will give us like the pieces that we need probably to like start visualizing those later, or visualizing what do I want to see, what do I even want to do, that I haven't really thought about. We could probably look at the weights on the good case and the bad case. And right, I forgot. We had just said that we were going to train the good case divide all the weights by 255 and run the original unmodified image through there and see if it works better. Okay, so here we'll say load weights from success case and modify for failure case, I guess. Not a very good message, but we get it. Okay, so just okay, let's add everything. Checkout branch December 24 and git commit -m checkpoint, because we've like got some like code in there that's like actually reasonable and useful, and I'm about to do something that's not reasonable and useful and we don't accidentally want to keep around. And I'm just gonna say, when we load the weights, can we like divide every weight by 255? So I think print net named parameters. I just want to see what we have in here. I think it's like layer1.weights or something. Oh, here we go. File exists error. So here we can try here and accept file exists error. And in this case, we will say, please specify unused. Please specify new output directory. And maybe then we also log the exception. Like this. As E, I think is the syntax here, and then we just return. Okay. Please specify new output directory. Nice. Okay. And what was I doing again? I already forgot. Right, I was gonna specify we were gonna specify a new output directory and output dir temp. And this is supposed to be a dash, not underscore, of course. And here we printed out our state dictionary. Great, this is what I was looking for. So we have linear 1 weights, and theoretically if we divide all of these weights by 255, we should be able to go back to like our old way and it should work okay. So I'm gonna revert this commit where this is where I did the change to like move everything from 0 to 255 into 0 to 1. So I'm just gonna revert this to go back. And now when we load the weights, I'm gonna load the weights and just divide everything by 255. So net linear 1 weight divide equals 255.0. Is that like legal? Is that, oh, oops, I should do this after loading. We'll see. arm-r temp and this. There we go. Leaf variable that requires grad is being used in an in-place operation. So he doesn't like that. Can I like just like adjust weights? PyTorch manually adjust weights. Because he's not liking it. Oh, you just say with no grad. So because this error is basically saying like, hey, we're trying to track gradients for these guys so that we can like do neural network things, like check how much they affect the output. And if you just like assign them, we can't fucking track that. But if we just say, hey, fucking stop tracking for a second, Torch no grad, hey, fuck you, don't worry about it. Maybe then it'll work. And it looks like it did. And interestingly, it looks like our loss matches what we saw before. So if we go back into our like temp thing and we look at this, oh, it looks like shit actually. Okay. So that's good, I guess, by some metric of good. I would have thought that by dividing, okay, how do I say this? So we have inputs in the range 0 to 1. All we did, all we did was, how to say this? Each pixel of our image is hooked up directly to the neural network. If I take the multiplier for those inputs and divide them by 255, then I would think that multiplying the input by 255 should result in the same thing. So, right, we have like pixel values in the original, you know, we have like 255, 255, you know, or we'll just say our pixel is 255. When we trained, we mapped this to 1, and we mapped 0 to 0 linearly. And so we're saying like when we train on this, this gets fed into the neural network, and the neural network is like, I'm going to multiply this by 1.0, right? And so then the output of this multiplication should be 1.0. And so I would think, hand wavy, that if I take this step out, then I'm going to have 255 here. And I would just think that if I did 1.0 over 255, I would still get 1.0 out this side. And so the question is that true? It looks like maybe not, because like this output is not what I'd expect. And why? Why is that not working? So let's see here. We might also want to like actually not do any of the actual training here, just in case, right? Maybe our one step of optimization was like fucking shit up. So let's try loading with our initial weights, output to temp. Yeah, that seems reasonable. And oops. Oh shit. We just like ripped that guy out like a million times over, but okay. So it was the fact that one iteration of training just like absolutely fucked our output. Because let's just here, we'll just fucking return here as well. Okay. One more attempt, just to double check. So here, first iteration, yeah, perfect. He matches exactly what we had before when we were in the range 0 to 1. So it looks like the training process, even with one iteration, not sure if I understand the problem correctly, but you cannot just scale your input because of the transfer function that makes neural networks nonlinear. Which transfer function? So my inputs, I would think, if I understand this correctly, I think I'm not explaining this very well. So you saying that you're not sure if you understand the problem correctly is like a good feedback, because I think I'm not doing this justice. But I would think I have a pixel that I've if my pixels are in the range of 0 to 255, so the brightest pixel I can come up with is the number 255. I trained my neural network that's just input, multiplier, output, essentially, for this pixel, but for every pixel. This is like some like multiplier M, and then there's some bias B at the end here, right? And when my input is in the range 0 to 1, this works great. And when it's in the range 0 to 255, training sucks. So my thought was train in 0 to 1, right? Divide these multipliers by 255, and then run with these inputs. And what we did just see there is that that works if I did that experiment correctly. But as soon as I start training from that state, it immediately gets fucked up. Right? So like what we have here is I've disabled all training code. And if I just do one iteration of training, don't even touch it. One iteration, only one, which is like very few, right? We've been doing like thousands. If I do one iteration, he got absolutely fucked. Right? Just like at signs everywhere. And so why would that be? Let's just double check. Check off that one step of training and run him again. And yeah, he looks good again. So what might be interesting is to visualize like what is happening between those two. So let's see what happens on one iteration of training here. Oops, I think this timestamp was wrong because I think I read the wrong one. So here we can say, what happens in one iteration training? What happens here? So let's double check that our labels are okay. So let's just quickly run our visualization again, just to double check. Yeah, so those labels that are getting generated seem totally fine. This is exactly what we want. And I guess what we should let's after one iteration, we'll check the loss before and after. And if I understand correctly, that one iteration should just tank our fucking loss. That seems reasonable. So we can say print the loss no matter what. Do training. Here's all the training code. Stub out all of this like saving stuff. All I care about is the loss right now. And we'll say if I is equal to 2, return. Just 2 iterations. Let's just see what happens. So we train, we load an initial state dictionary that was pretty good, and boom. So that's interesting. We do see that we go from like pretty fucking good to pretty fucking shit like immediately. Which is kind of interesting. So I wonder if it's just that the learning rates need to be extremely low for this case. You could imagine that if, how do we say this? Here we have weights that are either like, we're saying that we're dividing our weights by 255. And it could be that like you have like some function of weights, right? You have like these like trainings are like function of like weight 1 and like some more stuff. But we'll like, imagine like the one-dimensional case around. Let's say we only had one weight. You might have like, you know, something like this, right? And like your gradient, I think you're like, I am right here because my weight is this. And it's like, which way do I go to get a lower number? Then I go down the hill to over here. And it could be that like your gradients, like the slope of your input, they might be like not 255 times smaller or something. And if we're like step in this direction, if our weights have to be 255 times smaller, these steps also have to be 255 times smaller. And maybe like the learning rate also just needs to be 255 times smaller for it to not just like fuck itself. That seems possible. I feel like that doesn't make sense to me intuitively. I would expect that like gradients should have different slopes. For like, I would think that if all my numbers need to be smaller, my hills would be smaller as well, but maybe not. Maybe not. So let's start by just doing the stupid thing of dividing. Basically, like the large learning step is shooting you past the minimum. That's my guess, right? And my guess is that in the case where my inputs are much smaller, the same large learning step just has much less of an effect. Hand wavy. I don't know if there's like a linear relationship between learning rate and stuff. I don't even know what the learning rate is, to be honest, right now. Like I don't have like a good mathematical feeling for that. But let's just see. Say we like step it down a lot. So here, after our one iteration, our loss is a lot better, and it might be interesting to try to train for like go back to training for like 1,000 iterations. But with the learning rate really reduced, and we'll see if like the results are still reasonable. Maybe 1,000 is too many, but let's try like maybe like 200, just so that we can like get results reasonably quickly. So in here we have our first iteration, and we should be somewhat soon seeing a 200th iteration. Okay. So here we're actually seeing that it is progressing towards the right answer. Before we were seeing it just absolutely fuck up our results, but we are seeing it progress towards the right answer, which is interesting. There's something that I'm not like intuitively understanding about this. So maybe what might be interesting is like visualizing the gradients in both of the like 0 to 1 normalized input cases and 0 to 255? Maybe they're the same. Maybe. So I guess we can go back to training for one iteration. If I is equal to 2, return. And can we just, or even if I is equal to 1, we only need one iteration. And maybe we can like look at the gradients in here and see if they're the same in both cases. Yeah, let's do that. And also while we're here, maybe it makes sense to add a flag to normalize the input so I don't have to keep switching back and forth between revisions. So normalized inputs will be like a store or action is equal to store true. So this is going to be like true if we pass the flag, false otherwise. And then here we will, when we create our image sampler, we will pass in whether or not we want to normalize inputs. And here we just say, at the end, probably, if normalize inputs, which we need to take as an input here. Yeah. If normalize inputs, self.image divides equals by 255.0, and self.image for comparison, the other one we're looking at. And then there's another 255 in here somewhere as well. Get labels for samples here. So here we say, if, well, I guess we say normalize inputs, we'll just pass it in for now. And multiplier here is equal to 255.0, but if our inputs are normalized, multiplier is equal to 1.0, and then we use multiplier here instead. Okay. So we should be able to just train both scenarios now. So let's put the learning rate back to its original thing. And we will start. Right now we do one iteration and quit, but we still want to print the loss. And so what we should see here is if we pass no normalized inputs, the loss is big number, man. Hold on. We are failing because we need to store the normalized inputs thing and pass it into our label generation. This, I think. I don't know, something like that. So here we have normalized inputs is a bool, and then here normalized inputs is passing here. There we go. Okay, so there, our loss after one iteration was 1.0, which is kind of odd, even with normalized inputs not passed. Float cannot be cast to the desired output type byte. I feel like I'm missing something. First of all, I thought that the loss... Oh, no, it was after one iteration where the loss was really bad. Or after two iterations. So here we want to do I equals 2. So with normalized inputs not passed, our number got big as fuck. Okay, cool. And then we just have to fix the normalized inputs case, which means he doesn't like this like self-image divides equals 255. So maybe, which I thought we were doing, well, I had done this before. Maybe it's self.image equals self.image over this. Maybe it likes that better. It doesn't like it in place or something. Yeah, for some reason that's okay. Okay, cool. So, yeah, that looks pretty good. So in the case where we normalize our inputs, our loss seems reasonable. Like it like stays close. But in the case where we do not, he like explodes. Okay, so now I wanted to compare the gradients in those two cases. So I guess we can say, how do we do this? On the first iteration, we want to look at, after we run our backwards pass, that computes all of the gradients that all of our parameters have relative to the loss. So data dot, no, not data, network, linear 1, which is our like parameter, the only the only stage of our network. He's going to have weight, and we can look at the gradients of these guys. Okay, sure. And they are small and then big. But that makes sense because the second one where loss is really bad, so the gradient's getting bigger makes sense. And if we normalize inputs, our gradients are interestingly like, are these consistent? Yeah, they are. So with normalized inputs, after the first iteration, they're actually larger, which is actually the opposite of what I would have thought. I would have thought that with non-normalized inputs, the loss would get so bad because we were taking greater steps. But maybe we're only seeing like stuff around the edge. And this is for like every sample we pass in. So it might depend on the sample as well, actually. So I wonder if it makes sense to try to like visualize the gradients given a specific sample or for a specific sample. Or maybe like we want to see like what's like the maximum of all of them. That might be interesting. Yeah, let's look at like max. Is that not a function I can call? It is. Okay. So with unnormalized inputs, the maximum gradient was 0.3. But the maximum with normalized was 0.15. Okay. So there is something about like we're going to take a bigger step somewhere, hand wavy, with non-normalized inputs, which makes sense to some extent. Might be worth printing the max and the min of the absolute max. I think what I want to do is I want to maybe do like a histogram, show like all of our gradients and kind of see what like the like distribution of them is. And that might give me some clue. So maybe we can look at what do people use? Like matplotlib is probably what I've seen. Python plot histogram. Yeah, matplotlib, pyplot, histogram. Where I can look at the bins. So I guess I have all of these gradients. And you could actually do like gradient per pixel, but I think we don't really care. I think we just care about distribution of gradients like as a whole. So we probably like pull in matplotlib, we recast our gradients to like a linear just list of all gradients, and then we put those into pyplot and we just see what comes out. That seems reasonable. So I think that means that we have to nix shell -p python 3 packages matplotlib would be my guess. Pull this guy in. Okay. And then if we, what do we do next? We open up our training script again and we say from matplot or import matplotlib pyplot as plot. And I think that you can just say we have our gradients. Wait, grad. What's his shape? It's probably something related to like the number of samples and the number of inputs. So he has 228 for each of the 5 outputs, right? So for each pixel, for each output, he has a gradient. And so we can just say reshape -1. Like, is this legal? I don't actually know. He's missing a close bracket. Nice. Okay, so we'll try it again. So tuple object has no attribute shape. Oh, I just put this on the wrong side. Oops. Brackets are hard. Okay, cool. So that reshape is legal, and then we should just be able to plot that. So we should be able to say like plt hist this guy, but probably to like a numpy array, because pyplot probably only wants to work with stuff on the CPU. And then probably with normalized, like, does this, nice. Okay. So with normalized inputs, what is our like bin width here? Or maybe let's like, can we like increase the number of bins? How do I get out of this? So the histogram, I want like bins is equal to like 50 or something, just to like get more resolution. So I go here. Oh, fuck. Hist, or bins is equal to 50. I want 50 bins, baby. Okay. So interestingly, we have like a lot of samples in very small ranges. And can I do this again, but without normalized inputs and just compare? That's interesting. So what does this tell me? It tells me that in the case where we have non-normalized inputs, it's trying to change more? No, that doesn't tell us that. So here, actually, there's like a lot of things that like aren't changing by a lot. Then some things that are changing by quite a bit. Let's think. Can we like think about what each of these, what is like each sample in this scenario? Each sample is how much does 1 pixel times 1 pixel times some weight. How much that change to weight a particular character? Okay. So when we did this the first time, we did notice that okay, hold on. Let me break out of this loop. We saw that, I think that if we let one training iteration go through and then printed the image, I think we just saw like a fuck ton of @ symbols, which is our like brightest pixel. So I wanted to say, before we return, render the full image. Right, we render the full image, and let's just see if I like get something out of that. So I don't want to run this plot anymore. Okay. Oh, we got all colons. So it might be interesting to see how the weights for a specific output change, right? Maybe the colon is like where all of the big changes are, and maybe there's something interesting about that, maybe. Hey man, quick question. I'm not sure the right person to ask, but I've always wanted to train an AI model on voice samples and have it act like text to speech. Do you know if that's possible and how long it would take? I'm sure I'm sure it's possible. My response to anybody who's ever asked me if something is possible, especially at work, is anything's possible with enough time and effort. But I've always wanted to try. So you want to train an AI model that takes voice samples and have it act like text to speech. I imagine that's not a trivial task. Hand wavy. Audio, you would probably stitch in like samples over time and try to train that to correlate. Okay, my guess, hand wavy, is that would take a lot of data and a fair amount of effort. But I wouldn't say don't do it. I'm sure that if you start like Googling, like, certainly somebody's done this before, right? And I'm sure that if you start looking at like research papers for speech to text, or I think I've actually, you know what? I've done this before. I'm just remembering. I didn't train a model, but I fucking used one. Let me see if I can find it. What did I do? Because once upon a time, I thought it would be really funny to try to like corrupt text by doing speech to text, back to text to speech, back to speech to text, over and over again. And I thought that would be funny. And I did that somewhere. TTS Looper. Yeah. I used something called deep speech. So I would probably, if it were me and I was trying to do this, I would start looking at something like this and see, how did they train it? What, like, I'm sure there's like ways to like get like graphs of research papers, and you can say like, well, which papers are like similar to deep speech, and like you could read those, look for related projects, etc. But I think it's all about like, I doubt starting from scratch. I think that if you were starting from nothing, it would take you a long time to get to the right answer. And I'm sure that there's lots of people that have already tried this. So I would start by looking at state of the art, personally. There's Mr. Nothing. There's any benefit of doing this processing with mal over post processing grammatically, with ML over post pro? Are you talking about the text to speech, or are you talking about what I'm working on? ASCII. Okay, so I think at this point, for sure, no benefit, right? What I'm doing right now is just taking brightness values. But my suspicion, which I think that it'll be fun to kind of try to prove at the end, is that we could get like locality of pixels. Like, how do I say this? If you have like a sample that has like dark in the very dark in the top left and very bright in the bottom right, I suspect that there is a better match for this than just adding up pixel brightnesses, right? And I suspect that if we were to compare every glyph to this sample, we would find a good answer by some metric of rules, right? We would be able to like say like multiply the top, like take the difference between this and each glyph and see which one's smallest, maybe try blurring one, maybe try like, we come up with all sorts of rules. And my suspicion is that if we were to try to encode that into a neural network, we would get the same answer for less computation. Hand wavy. That's kind of what I'm suspecting, right? Because if we had some sorts of rules, we're gonna have to at least multiply every single pixel by every single character. And if we then in the future end up with a network that has like, every pixel to every character, you might be able to have some sort of like intermediate thing in the middle that's like only like 10 things. And so instead of having to do like m times n, you might be able to do like m times 10 and 10 times n, which I think might end up being smaller in some cases. I haven't actually like proven this at all, or even like really thought about it hard. I just suspect that you could do this. And I also suspect that since these are mathematical rules of like, I'm going to multiply this pixel by this, and this pixel by this, and this pixel by this, I suspect that there's a lot of like multiplications in here that will end up being close to zero, right? You can imagine like in this scenario, you have a glyph that like matches this. You can imagine this glyph, if it matches this, it probably doesn't care about anything other than like the difference, like this hard edge right here. And so I suspect that you could delete a bunch of weights and still get the right answer, which would like heavily reduce the amount of computation. But I don't know. That's what I'm more using this as an excuse to explore the area than I wouldn't be surprised if we got to the end and we found out that this whole project wasn't worth it. And I think that would be a valuable end result. Anyways, what were we doing again? I got distracted. We were plotting out the histograms of gradients after one step for both normalized and unnormalized inputs. And we were trying to understand, why are they so different? So maybe it might be a little interesting to look at the gradients for, what the fuck? I don't know if you guys saw it, but there's like some like shadow text in there. There's like, that's really weird. I've never seen that before. Okay. So we were trying to see why are the gradients so different? Because, the gradients are going to be really different because our inputs are, hold on, thinking. Oh, the gradients should be very different for the 255 case because our data isn't normalized, and the weights that we loaded were for normalized. But when we loaded the weights, we divided by 255. Right. Sorry. Brain's catching up. I got distracted. Okay, so we loaded weights, we divided them by 255, but the gradients are still larger. Even though the steps, we should be in almost equivalent spots. And we saw when we do one iteration that we just club our output. And so it might be interesting to say, well, is it the weights for one specific character changing a lot? Maybe. That seems possible. So can we maybe say, instead of reshaping this, and we'll just look at the gradients for one of the many characters. So I think that we can just say gradients for 0 and see what those look like. And one of these is presumably, maybe one of them is bigger than the other. So the gradients for the first character, the one for the darkest character, is maybe in the range, mostly in the range -0.05 to 0.05. And I think I have to close this. What about for the brightest character? I think that was the brightest character. These are the gradients for the brightest character are much bigger. Hand wavy. And what about the second brightest character? Second brightest character, we see the same as for the dark character, not very many changes to be made. And what about the least or the second brightest character or the second least bright character? Okay. So that's kind of interesting, right? We're seeing that the gradients for bright characters, i.e. the biggest numbers, are very large. Now, this is with unnormalized inputs, and let's check with normalized inputs again. And I want to check the brightest one. And in this case, all of the gradients are trending in the same direction. I don't know if that means anything interesting. It might. That means that for all pixels, for every single pixel, our gradients are trending in the same direction. We're saying we want them all to be smaller, which makes sense, I think. Or maybe it's saying they want them all to be bigger. Okay. So, does this teach us anything? Does this mean anything? I don't know. Because the fact that the problem is how do I say this? The problem is compounded for the biggest number. Let's look at the gradients for smaller inputs. It teaches how to draw an histogram. Yeah, that is one of the things that we've learned. Oh, interesting. Okay, so it looks like for the smallest character, for the darkest character, we're trending in the same direction for all inputs when we normalize. Okay, wait. This is kind of interesting. So when we look at normalized inputs, it looks like all of the gradients are in agreement with each other. For each character, we're either trending in positive or negative. But also the numbers are much smaller. So it looks like there might be some confusion in general about each number. Sorry. So for the normalized inputs, we are saying we know that we want to go this way. And for the non-normalized inputs, they're kind of just wow, we could change a lot here. But it doesn't give me an intuition as to why that's the case. What I'm trying to build up here is I'm trying to say I know that when I've set my numbers in the range 0 to 1, that the network performs better than when 0 to 255. But what I don't understand is like why, and if I don't understand why, then I feel like I'm gonna make this mistake again later, and I don't think that just like randomly fiddling values makes sense. Okay, so looking at these gradients, not teaching us, I feel like I'm not really learning much from that. What if we looked at the weights themselves? Out of curiosity, why do I divide? Fuck, you're right. You said, why do I divide it by 255 every time? Shouldn't that depend on normalized inputs? And I think it should. So all of those experiments that we just did were fucking bullshit and not right. So just scratch everything in the last 15 minutes and we'll try again. Because you're right, we should only divide this by 255 if we are not normalizing inputs. So if... Good catch. If normalize inputs, then we do this. Okay, now we can look at this again. So our gradients still look the same. But let's double check here. On the second iteration now, it does look like shit even though we normalize inputs. So that's a good clue. We should confirm. This should be if not normalized inputs. That's why. Aha! Okay, so here I need to close this, F5. Okay, sorry, that looks good. And let's look at our histograms again, but this time just look at it across the board. So we reshape this into like a linear thing. And for the normalized case, oh, that looks so much better. Okay. That makes so much more sense. Okay, for the normalized case, there's like almost no movement to be had. Like almost none at all. Everything's like pretty damn happy. But for the normalized case, it was not. And I guess it's worth checking, is there another bug that we could have maybe introduced in the non-normalized case? I think that this was the only one. Okay. So why? Why? They're saying that changing the parameters has a larger impact on the output if the inputs are non-normalized. Is that correct? If the values are in the range, if values are in 0 to 255, gradients are big. If values are in 0 to 1, gradients are small. So that means with larger values, weight changes have bigger impact on output. Okay, you know what? I think that makes sense. With larger values, weight changes have a bigger impact on the output. That is true, because the same weight change is going to result in a way bigger swing in answer. Yeah. Okay. So then, just the concept of having to lower my learning rate in that case also makes sense. Because... So I wonder if all of this just means that if I trained my original thing with a much smaller learning rate, if my results would be approximately equivalent. So I just don't normalize my inputs, and I just set my, we'll say LR is equal to 0.001, and we'll say if normalized inputs, LR, or if not normalized inputs, LR is divided by 255. And I wonder if we can train that and see similar results in both cases. Yeah. So let's train with no initial weights, with no normalized inputs, and oh fuck, I need to disable this like Python plotting shit. Fuck. And we also need none of this histogram shit, and we're not returning anymore, and we're checking if I percent 500 is equal to 1. Then we print the loss, and we save it. Okay, so let's see if this training would gives us like something reasonable. And we just gotta wait a little bit. Just gotta wait a little bit for a few iterations to go by. I think you defined it, but didn't use LR, by the way. Yeah, that would do it, because it did look like shit. Let's try again, Good catch. Man, it's so sick when other people look at my code, because when I code and I just like make these mistakes, you guys are just like, hey, you did something really fucking dumb. And when I do it by myself, it takes me, you read a bug and it just takes like half an hour to find it. It's great. Okay. So let's give it like maybe like a couple thousand iterations, with non-normalized inputs, and then a couple thousand with normalized, and see if the results are similar. I guess our gradients were not relative to 255 though, right? They kind of like exploded by, like we were seeing like 0.3s and 0.0003s. So like it was like almost like multiple more orders of magnitude. So it wouldn't shock me if the learning rate has to decrease by like the square of something. Yeah, because this is still shit. But maybe if we decrease, like divide it by 255 twice. Let's just, just hand wavy squares come up sometimes. I'm not like saying that is a squared relationship, but it might be exponential instead of linear relationship. I'd have to double check the math behind. While not good, LR divided by 255, yeah. Because this actually does look maybe more reasonable, but we'll see. We'll give it a few more tries. You could also do something like, I guess the learning rate, I guess what we've kind of just like proven to ourselves is that gradients are heavily affected by inputs. And so I guess that kind of means that your learning rate, like it might be worth like discovering a good learning rate when you train instead of trying to pick one by hand. Hand wavy. That seems like possible. Okay, so this is just still shit when we divide by 255, so, or when we divide learning rate a lot. So there might be something else to it. But I think we're so close. I feel like, yeah, okay, so it was interesting that it's still just getting like absolutely fucking trashed. It might be worth also double checking just while we're here, that our labels are reasonable in both cases. How is the loss calculated? Right now, the loss is, we check which character is bright, like matches the brightness of the image. So we have like this like character map that basically is just like linearly increasing with brightness. And then we say, we sum up all of the pixels in a sample, and we basically say like what percentage of like the maximum brightness is this, and we just pick one of these to be like correct. And then we do like a, cross entropy loss, where the correct answer is defined by which index we returned. And I guess we should double check that our labels are being generated correctly in the non-normalized case. So let's go back to our visualization. Is it a grayscale image? Yeah, it is. So our visualization now needs to pass in normalized inputs, which is going to say normalize inputs with action is equal to store true, and the required is no longer true. That gets passed into the image sampler. And this gets passed in here probably, if I remember correctly. Yeah, okay. So I just want to double check that if we visualize with non-normalized inputs, it looks okay. And with normalized inputs, the characters that we select, like our label generation is good. So we can be fairly confident that the training process, well, fairly, we can be like more confident than we were a few seconds ago that the training process is working okay in both cases. So last time though, when we trained with initial weights, non-normalized inputs, let's see if that training works okay, right? Maybe it's having a harder time getting into the correct initial state, but if we give it the initial state with the learning rate with a smaller learning rate, does it like at least improve from that state? Because I think when we were looking this up before, we saw that parameter initialization was in some range for linear. I remember seeing like a negative square root something to square root something. Yeah, uniform -1 over square root in features to 1 over square root in features distribution. So in features, I guess, is like the number of inputs, and our like initial state is going to, like, maybe we need it to be in like a much smaller range in the case where we're using non-normalized inputs because we know that we want something tighter, maybe. And so maybe if we like kick it into that state by loading our initial weights. Yeah, okay. That could be it. So we divide our gradients by 255 because our inputs are 255 big, but maybe we need to like initialize with a tighter range, which is kind of interesting. It could be that like the default parameter initialization in PyTorch is expecting like it might be like tuned for some expected input. That might be reasonable. So maybe what we can do is we can specify our own initialization. And what do we do with that? Skip initialization or specify our own. And in our own version, we just initialize the weights randomly in a much tighter range, because all of our values should be smaller. Or we just initialize them to 0 and see what happens. That kind of seems reasonable to me. If we skip all of our initialization, do they just start at 0? Skipping init. Not sure. Maybe we just have to initialize them 0. Could the brightness range of the characters not match the brightness range of the pixels? I.e., every pixel is brighter than any character. The way we're doing it though, here let me just double check it here. I'm pretty sure that our label is generated as relative to the total input. So get labels for samples. Here we say to look at the samples, we sum up their like every pixel width height, and then we divide that by the maximum brightness multiplier times height times width plus 1 to basically say like how bright are you from 0 to 1. Yeah, so we're like doing some normalization here, so I don't think that there's any like bug in the label generation for the like normalized versus non-normalized case. And actually we did double check, we did prove here in our visualization that our label generation is like okay. So I'm not worried about that, I don't think. Okay, yeah, let's try initializing the weights manually and see if that affects the difference between the two trainings. So here, instead of loading this guy, in the case that we don't provide initial weights, can we just set all the weights to 0? I think you might have to do like say assign 0 to all values instead of reassigning this like label. I think. I'm definitely new to this, but it seems odd that the loss decreases while the image is getting worse. But I most likely misunderstanding loss. Yeah, there does seem to be something odd about that. I think I agree with you. But it could be that like it could be like weighting towards something wrong. Like it might be like averaging out errors in a funny way, possibly. But you're right. That is something worth thinking about for sure. Sometimes we see the loss grow as it gets worse, but I think it could just be that like 1.5 is like not a very good loss. Any tips for an ML engineer? I have 2 years experience as a software engineer degree. I'm very interested in this field. Any useful tips? I will say, okay, so I did work at a company that did AI. I was not an ML engineer, and I don't know. I honestly don't have a good feel for if I applied to somewhere as an ML engineer. I don't know if I would get the job, so I don't know if I'm like the person to ask. But I think with anything, if you want to break in, you just have to do the thing. So I think coming up with a project and trying it and like trying to prove to whoever you're trying to get employed by that that was like worthwhile and proves that you have knowledge in the area. I think that that's probably like, yeah, I think the only way to what's my current role? I am unemployed. My current role is Twitch streamer that makes very little money. I'm taking some time off, so yeah, I'm not really. Yeah, I don't think I'm the person to ask, but yeah, practice always. Okay, so let's set all of these weights to 0, and isn't this what they are doing? Probably. I think that they're probably, yeah, I think that like this is probably similar. I just think that I like I was doing some like OpenGL rendering stuff a couple streams ago, and that's like something that like a game engine developer would do, but I have no idea if I would be able to get hired as a game engine developer. It's just like we're doing stuff on this stream, people are watching me bumble through things like an idiot for some reason, and I don't know shit. But we're learning together. So, yeah, I just don't have a good feel, unfortunately, for how this stuff translates. Okay, so we were going to try initializing all of our weights to 0 and see if we get more consistent results between the two. So let's try training with normalized inputs. Output, dir, temp. Normalize inputs. I know what a vertex array object is. Now hire me. Yeah, perfect. You're hired. Okay, so instead of using randomly initialized weights, we just manually set them 0. And let's see if after some period of time, our normalized input training gives us a reasonable answer. If it does, then we can try again with the non-normalized inputs and see if they're like equivalent to some extent. Okay, so after 500 iterations, I'm like reasonably happy with that. We see some like @ symbols in the corner here, right? We see A's all over, and we see like reduced brightness in the area with the hill. For those of if people are just jumping in, we should probably show the sample image that we're trying to replicate as well, right? So that's looking pretty good after 500 iterations, and maybe even up to 1,000, and that's also looking like decent. So let's compare this to now with doing that with no normalization. So let's just back up this folder as like normalized with zeroed weights. Okay, and we'll try again without normalized inputs with zeroed weights, and we'll see what we get. And fingers crossed that it's good, because I think that this is like, I feel like I get it right now. And if it looks like shit, then I'll feel like I don't get it again. And I want to feel like I get it. And so like, yeah, here we go. Okay, so that still looks bad. Loss 1.3. Here we got to like 1.0 pretty quick. Oh no, that was the wrong one. Here we're up to 1.19. So let's give it a little more time, because it could be that like the weights, our learning rate might have to be reduced even more. But I am definitely less happy with this version. But maybe we should check. Let's check actually after the first iteration, what our gradients are for each of them, and scale the learning rate accordingly. So maybe we say linear net linear 1 weight dot average, or sum. Maybe we sum it all and we divide by, I guess we don't have to divide by anything, so we only care about the ratio between the normalized and non-normalized case. So we'll say print, and we don't want weights, we want the gradients, sorry. We want the sum of the gradients. Sum of gradients. So in the non-normalized case, we get a sum of gradients of like something in the range 0.0017 for the first iteration. What about in the normalized case? Normalize inputs, I think is what we called it. So we are going from like 2 zeros to 8 zeros, which means that a 255 division is like not close. We want like 1e negative 5, right? 2 zeros to 8, that's 5, 6, 5. Let's try 5. Assuming that the learning rate is like a linear thing, which I actually am not sure of at all. Okay, so we will stop printing this, and we will train. And maybe now, hopefully, we will see that after 500, what's like we're hoping for losses of around like 1.08. We will see. We will see. Come on, buddy. Here you come. 1.5. Still not good. Still not good. Okay. I guess what we should actually look at is also, so what have we done? We've started from 0 in both cases, assuming that will, if we reduce the learning rate with our higher values, which create higher gradients, which create higher, how to say this again? In the case where we have bigger inputs, which create bigger gradients, which create bigger steps, and then we reduce the learning rate. We thought that if we zeroed everything out, that maybe those would like cancel each other out if we reduced the learning rate and started at the same spot. I'm also recently realizing that I didn't zero the biases, which might have a major effect, so let's just zero out the biases as well. And you're saying try without changing learning rate again, just to be sure. Oh, I'm an idiot. Wait a second. Oh no, this is fine. So we are just dividing by 255 here, but that'll still be 0, so that's okay. That's okay. That's okay. So here you want to say try same learning rate, but zeroed everything. That's possibly reasonable as well, actually. That's worth looking at. So here we're seeing 1.6 after the first iteration. And I do want to say that I think that we do see something different when we normalize our inputs with everything zeroed. Oh, no, that's the same. Oh, okay. Okay, so we see 1.6. And I'm going to increase the frequency again from 500 to 200, just so that we're waiting so long between feedback, and I want to get there a little quicker. Okay, so with normalized inputs, after 200 inputs, 200 iterations, it looks shit. So we'll give it a little more. After 400 iterations, it looks a little better, right? Those are starting to look okay. And so maybe we're looking for, the loss there is 1.2 to 1.21, 1.17. That's starting to look okay. Let's try again with non-normalized inputs and see if we get we have the same initial loss, which is good. That's a really good sign. That means that all of the same predictions were made on the first iteration. But here with our learning rate not reduced, we're getting fucked. immediately, right? We're seeing like 1.6 to 4.4. Okay, so let's try going back to deleting this, shrinking learning rate by a lot. And we go from 1.6. We want to see it go down. And the first, we saw around a 0.4 decrease. This is a much smaller decrease, but it is a decrease. It's possible that we're decreasing it by too much. So let's just reduce this like 1e -3 or something. Reduce learning rate a little less. Maybe we're just not learning fast enough. Because it could be, I don't know if learning rate and gradients have like a linear relationship. So it could just be that the learning rate has to be reduced by like less than I thought. Or more than I thought. Who knows? I guess it's probably worth, we'll let this run for a little bit, because I do want to give it some time in case it just needs to break out of some shitty behavior. But I do wonder, like, I don't really know what these optimizers do. So can we like look at like PyTorch Adam? What is he doing with the gradients and the learning rate? So he's got, oh my god, gamma, beta, params, objective, weight decay. So our weight decay is 0, so we don't have to worry about the lambda here. We have these guys, which are params and objective, which should be the same for both our training cases. And so betas are 0.9 and 0.999 learning rate. Oh, I guess the params and the objective, I guess it depends. I don't actually know how cross entropy loss works either, so that might also be interesting. Like, is our... how do I say this? Cross entropy loss. I actually don't know what I'm even trying to say because I'm so lost on the subject. So what is this guy? Cross entropy between two probability distributions over the same underlying set of events. So we are summing up distributions, PQGs. That's a lot of math. Is there like a more like noob idiot way of explaining this to me? Criterion computes the cross entropy loss between input logits and target. It is useful when training classified problems with CZ classes, which is kind of what we're doing, if provided the optional argument weight should be a 1D tensor, blah, blah, blah. The input is expected to contain the unnormalized logits for each class, which I think we saw as like 1 over log something. Which blah, 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 blah. What does it do, though? What is a cross entropy loss, you know? I assume that I think it takes like big number, it's expecting like 1, 1 and a lot of zeros, I guess. Right? Like all of the classes should be saying I'm 0, except for the one that we want, which should be saying 1. So it could be if there's like some sort of like weird relationship here as well between like, maybe the cross entropy loss is like much worse for bigger numbers or something, for the same input. Maybe. Yeah, this is still shit. Hi, how are you doing? This is my first time here. What is your background related to ML before I start talking random messages? So I worked kind of with machine learning for a couple of years, not as like an ML engineer, but kind of like in their code bases a little bit. Kind of working on like training data and stuff and like debugging of training them. So I've got like a fair amount, but I mean, in terms, you can tell I'm pretty lost when you're hearing me talk here. But I'm trying to debug this very simple neural network. But yeah, I've got a bit of experience, but not a ton. Okay, so this guy's clearly not getting better. And I guess we could maybe assume, I think that like given, okay, how do I say this? Given that when we trained with our inputs in the range 0 to 1, we got to a correct answer. I think that if we are not converging on a good answer here, maybe we should assume that we need to keep reducing learning rate because we know that we can get a good answer with the same inputs just scaled. And we know that our gradients were like much, much, much larger. Can we show again the gradient? I know that we had it somewhere. We printed the loss, or the sum of the gradients for our weights. That's what we printed. So we had, our network has one linear layer, and he has weights, and those have gradients, and we can sum those up. And it says sum of gradients. I know we already did this, but I forgot like the scale between the two. Net, linear 1, weights, grad, sum. Okay, he's saying that that's not callable, but I'm pretty sure it is. I think that my... oops. And we are still training here, so let's do this. Linear object has no attribute weights. Oh. It was the linear one... Weight? Weight, not weights. Okay, so in our first thing, the sum of gradients was negative 0.15 for non-normalized inputs. And for normalized inputs, it was extremely small. So, like, can we just, like, see what the ratio of these is? Python 3, we say this number over this number. So 0.0005. So it does seem like if learning rate is linear, timesing this by 0.0005, I would think would give us something that's like somewhat related. But my suspicion at this point is that they're not linearly related. So I do not really expect to see a good outcome by doing this. But let's just give it a second just to see, just in case. Okay, so 1.3. Yeah. See, we're like immediately getting into this case where like every single prediction is the same letter, which isn't what we were seeing when we did like our normalized training. Okay. Let's start with your first question. With an LR reduction, you are right, but at the same time wrong. You generally don't want to reduce your learning when you're stagnating or going back up your loss. Not every epoch. Yeah, I do agree that I don't want to decrease when stagnating. But I just feel my gut is saying that given that I guess I was assuming more that we were overshooting with our initial learning rate. But it does seem like it's stagnating here. So I do agree with you. It does seem like that's not doing what we want. Let's go up a little. Because like maybe we're just reducing it like way too much, I guess. Alright, let's see. Okay. So he's still reducing. We're seeing us approach what we were getting at the end of the last training a lot quicker. Which is good. Okay. Yeah, I guess I'll leave this one for a bit, see if he starts to look okay. I am starting to feel like I wonder if there's a different meta parameter we need to change due to the changing input scale. That seems very likely as well. I'm trying to decide like how far I want to go down this rabbit hole. I think, oh wait, this is looking like maybe actually okay. The ats in the corner are correct. And we're starting to see the hill. Oh, this is starting to look maybe okay. I'm going to like leave this one a bit. And if we can get to the point where non-normalized inputs get to like a reasonably okay answer, even if I don't understand the exact relationship between the learning rate and the inputs, if I get something, then I think that I'll be like fairly content saying that I think I like at least have like a feel for the problem, even if I don't understand it perfectly, right? The fact that our bigger inputs, increased gradients, so our learning rates have to be reduced, that all makes sense to me. What maybe doesn't make sense is how I would like intelligently pick a learning rate. But I guess trying like we got to that first one in our success case kind of just by luck, I guess. We kind of just picked a learning rate and it happened to be okay. You could maybe argue that like inputs that are smaller might be easier to tune in some way, right? You could almost argue that large changes are harder to debug. Or you could imagine that you want your weights to be able to have like a large range of like correct-ish answers. And in our case, where our inputs have to be divided by 255, like maybe there just isn't a large enough range there. So that could be like a reasonably okay rule of thumb to keep in mind. Yeah, I mean, loss is still decreasing. It is still decreasing. Just slowly. So it could be that we might even want it to be like a little higher. But can we compare this to what we previously said was pretty good? Okay, so this one is still clearly a lot better. After 1,000 iterations with normalized inputs, we're clearly at a better state than we are here. But I think we are still approaching that correct state. Yeah, he's definitely struggling more with these like A's. Okay. I guess the question is like, how long do I want to let this sit before calling it? I do think that I think I understand the problem. And so I think maybe what I'll do is grab a glass of water, let this sit a little longer, and then come back and check. And hopefully, if I let this train for just a little longer, we'll get to the point where it looks okay, and then I can call this like checked off in my head. So give me like 2 minutes and I'll be back. Back with water. Loss still decreasing. That's a good sign. Let's see. Is he looking? Let's at least see if he's trending in the right direction. So here. Oh yeah, we're definitely seeing like areas where in our correct answer they were all colons. We are seeing it slowly converge towards the right thing. A's are reducing, colons are increasing. I think normalized hit 1.12 or something after 200. Yeah, I think that like probably my gut says at this point it's almost like a game of tuning. Because before what we were seeing with like the unnormalized inputs, yesterday we were just like, what the fuck? It's just bad. And I think that now we're kind of seeing that it's bad but improving. And so I think that here we could probably say, if we came back and we try again, and we increase learning rate even a little more. So maybe instead of 0.05, we multiply it by 0.1. We'll double the learning rate. There's probably some amount that will result in similar behavior to our normalized training. So let's see, 1.6, 1.3. Let's 1.28. So it's almost like we want him to go a little faster. Well, it's hard to tell. You don't know if he's not going down because he's like flipping back and forth over the right answer, or because he's not learning aggressively enough. Okay. I know that this isn't a very satisfying conclusion, but I think I'm happy enough with my understanding here. It's not perfect, but I came in with the question of why the fuck does reducing my input space result in a better network? And when we looked at the gradients, we did see that like we have a much larger gradient for bigger numbers, and that makes sense. We're a bigger number, changing the weights less will have a much larger impact. And so we can probably assume that like I've heard as like a general guideline before working with AI that like things, you know, you might want to normalize your inputs once in a while to stop your weights from like exploding. And I think I like understand that advice a lot better now. Obviously we you know, it would be nice to be able to prove to ourselves that we could get the correct training. But at the very least, like we've at least seen improved results by like heavily reducing our learning rate from what we were seeing yesterday. I'm pretty sure. What might be interesting to you is plotting your loss and your learning rate and get a feel for what's a good learning rate. It would make more sense. Yeah, and probably also like allowing my learning rate to change over time. I think probably would also make a like be interesting, right? Like use like a proper like learning rate scheduler, and you might find we might just like automatically fall into something that's like kind of reasonable. Yeah, so I think that yeah, eventually we will have to pull up like visualizations for this stuff anyways. So, but I think not today. I think as of today, I think I'm happy. Um, yeah. So thanks for watching, guys. Uh, hopefully the next one is there's a little less just flipping back and forth between two things and a little more development. If you liked what you saw, I'm gonna stream. I'm not gonna stream tomorrow because tomorrow's Christmas. Merry Christmas, everyone. But we'll be back maybe not on Boxing Day, but maybe the day after. We'll be back continuing on with this project. If you are watching on Twitch and you miss a stream, there's a YouTube link in the Twitch description, and if you want to like, watch VODs and catch up, that's there. And if you're watching on YouTube and you want to come hang out, there's a Twitch link in the YouTube description. Yeah, thanks for watching, guys. Catch you in the next one. Bye!